All right, so what about images formed by way of refraction? Uh, so first off, I've got the figure here that shows just how rays refract going from water into air and how that changes the image location. And so when this is similar to the cat and fish question from the quiz last week. So someone in air looking into the water will see an image of an object that's closer to the surface. The image will be closer than the actual object. And then the reverse of that would be if you're in the water looking out into air, you're going to see an image location that's further away than the actual object location. And this expression right here, it's just the ratio of the indices of refraction that tell you how much further or how much closer the image is going to be from the surface. Now, the thing we're going to spend the rest of our time focused on is a specific application of refraction, and that's the use of lenses. And we are going to use something known as thin lenses. And what that means is that in reality, you've got this lens here, and your rays are going to hit the surface here and bend. Right, they're going to bend away from the normal. So let's try to sketch in a normal here. Yeah, it's kind of close. So our ray would bend towards the normal. Let's get that all the way to here. And then at this surface, let's draw the normal on this surface. Something like that. It's a terrible normal. And now this is going to bend away from the normal, coming out into air. And so what we're going to do instead of both of those changes in direction, we're going to instead say that this is a thin lens, and we're going to approximate the thin lens as though one refraction happens right at the middle of the lens. And so what we're going to do instead of these multiple changes in direction, we're just going to draw the ray coming in, and then it's going to refract at that lens plane. So we've got two types of thin lenses. We have converging lenses and diverging lenses, and the particular shapes can be slightly different depending on how the lens was made, but typically the biconvex or the biconcave for the converging and the diverging, typically those will be the drawings or the shapes that we'll be using for converging and diverging lenses. Right, now, the names converging and diverging are chosen for a reason. Converging lenses, so in this picture here, converging lenses will take rays that are parallel to the optical axis and refract, change their direction so that all the rays bend towards the optical axis. And in fact, they bend towards the optical axis in such a way that all of the rays cross the optical axis at the same point. And this is called the focal point. This is the focus of a converging lens. All right, so converging because any ray that passes through the converging lens will bend towards the optical axis. Parallel rays parallel to the optical axis, will bend towards the optical axis and cross the optical axis at the focal point. Now, what about a diverging lens? Same idea, but now instead of rays that are parallel to the optical axis bending towards the optical axis and converging at the focal point, now our parallel rays, right? So here's a set of parallel rays to the optical axis. Now instead of those rays bending towards the optical axis, they are going to bend away from the optical axis. Right? This is why diverging rather than converging. So those rays begin to spread apart. Right? These rays will never meet over here. So instead, what we do is we trace these rays back. It appears that these rays are all coming from the same spot over here. And that's the focal point corresponding to the focal length of the diverging lens. Right? So for a converging lens, rays parallel to the optical axis all bend towards the optical axis and converge, come into focus at the focal point. For our diverging lens, our parallel rays pass through the lens and diverge away from the optical axis. And when you trace those rays back, right, how much do they diverge away from the optical axis? Well, when you trace those rays back, they have to pass through the focal point of the diverging lens. And just like the examples with the spherical mirrors, ray tracing is a useful way to figure out where images will form when you have thin lenses. And so we're going to go through a quick sketch of the three principal rays that you can always draw if you've got a thin lens to figure out where the image of your object is going to form. So the first ray is this ray 1. So again, my object is seated on the optical axis. So that's, again, the typical way you start a ray tracing diagram. So you place your object, the bottom of the object on the optical axis, and then you place your lens here centered on the optical axis. So I've got my parallel ray to the optical axis. So I'm going to try to find the image of the top of the arrow. So the ray that's parallel to the optical axis, I've got a converging lens here. Well, that ray must pass through the focal point. Right, so here's our first ray that's been drawn. So immediately we know that the image that's going to form is going to be somewhere along this line. But we don't know where exactly because we need more than one ray to determine where that image is going to form. So number 2, for a converging lens, turns out for a diverging lens as well, when you draw the ray that passes through the middle of the lens, that ray continues on as though without changing direction. And so this is ray 2. So you can always draw ray 1 parallel to the optical axis, refracts towards the optical axis, passes through the focal point. Ray 2 passes through the center, and the effect of passing through the center is that there's no change in direction. And then 3 the ray that passes through the focal point on the near side, that ray will come out parallel to the optical axis as it passes through the lens. And you can see all 3 of these rays intersect at the exact same spot, so that's where the top of the arrow forms. And again, the bottom of the arrow, basically all 3 of the lines that I just drew, those are all exactly the same line for the portion of the arrow that's on the optical axis. Just everything passes straight through. So you know the bottom of the arrow is going to be on the optical axis. You just don't know where until you figure out where another spot on the object, where that image forms. And once we do that, we know that the image forms at this location. You'll notice that the image is inverted, upside down relative to the original object orientation. This means that we have a real image. And so for a converging lens, when your object is outside the focal point, the resulting image is going to be a real image. This is an image that is inverted. And our object distance and our image distance here are labeled in the picture. We use the same exact notation that we used with the spherical mirrors. And so look down at the second figure here, and we've got a diverging lens, and so we're going to do the same procedure. The three principal rays that we can draw so that we can figure out where does the image of this object form. So ray 1, parallel to the optical axis. And now this is a diverging lens, so rather than converging or bending towards the optical axis, this ray bends away. And how much does it bend away? Well, it depends on where the focal point is, because you're going to trace this ray back. So we know that the image forms somewhere along this line. We don't know where until we draw another ray. And so ray number 2 is the ray that passes through the center of the lens. And again, passing through the center, the net effect is that the direction doesn't change. And so if you look over here, say your eye was big enough for both of those rays to enter, these rays are never going to meet. They're diverging over here, right? The distance between these rays gets further and further apart. So what that means is you trace these two rays back. And for the green ray, when you trace the ray back, it's just on top of the ray. So that means the image is going to form right there. And if we want, we can draw the third principal ray. The third principal ray is the ray that passes, the ray that would pass through the far focal point if the lens wasn't there. So notice how I'm drawing that right there. So this third ray is the ray that would go along that path, but hits the lens and then comes out parallel to the optical axis. And then you can trace that ray back, and that also intersects right there at the same location. And so I'm going to clear up the rays just so that we can see the image. So we get an image that forms right here. You'll notice that the image is the same orientation as the object. This tells us, so it's an upright, it's a virtual image. We know it's virtual because the rays are physically over here, and they only appear to come from this side. So this is a virtual image. Again, object distance, image distance, using the exact same notation that we used with the spherical mirrors. So just like with the spherical mirrors, the ray tracing can give you a good sense of where an image is going to form. And if you're very careful about your drawing, the distances, using straight lines, then you can get a pretty good estimate for where an image will form in the magnification. But if we want to quantify image location and magnification, typically we'll use the thin lens equation. Right? So just like we could use it for our spherical mirrors, we can use the thin lens equation for thin lenses. And so the only thing that we have to be careful of here is sign conventions, just like with the mirrors. So our sign conventions for using the thin lens equation are that converging lenses have a positive focal length. So this right here. So positive focal length for converging lenses, negative focal length for diverging lenses. And so that means if you're going to plug in to the thin lens equation, the focal length, if you have a converging lens, that number is going to be a positive number that you plug in. And if you have a diverging lens, it's going to be a negative number. The other convention is that real images are going to have positive distances, and virtual images will end up having negative distances. That will come out just from using the thin lens equation if you plug in an object distance and a focal length. Right? If you solve for the image distance, which is a typical thing for you to do, if you get a negative image distance, that tells you that your image is virtual. It also tells you, looking at the magnification expression, it also tells you that your magnification would be positive because you're going to take the minus of a negative image distance. And so if your magnification is positive, it means your image is virtual. It means the image is upright. If your magnification is negative, it means your image is real. It means it's inverted. And again, the ratio of the image distance to the object distance is going to tell you whether the image is magnified or not. So a magnification greater than 1 would tell you that the image is larger than the object. A magnification smaller, between 0 and 1, is going to tell you that the image is smaller than the original object. Right? And the negative sign is telling us whether it's inverted or upright. On this last page, real quick, just some examples of what happens when you have a converging lens or a diverging lens. So this first picture, I've got an object that is placed outside the focal length. So here's the focal length of the lens, and our object distance is much larger than that, so it's outside the focal length. And when that happens with your converging lens, you are going to get a real inverted image. However, if you bring, in picture 2, if you bring your object inside the focal length, so here's my focal length, but now my object distance is smaller than the focal length for the converging lens. When you do that, notice how the rays that I've drawn when they pass through the lens, these rays are no longer going to meet on the right-hand side of the lens. Those are diverging. So how did the converging lens create diverging rays? Well, all of the rays still bent towards the optical axis. Notice this first ray was going this direction, and now it bent down. Now it's going parallel to the optical axis. This ray was going parallel to the optical axis, and now it's bent down. So each of the rays still bent towards the optical axis. It's just that because of where the object was located, those rays didn't bend enough for there to actually be convergence. And so what you have to do is trace those rays back, and you're going to get a virtual image. And this is basically what happens when you have a magnifying lens. You place the object just inside the focal length of your converging lens. You place your eye over here, and you see a magnified upright image. And so the last picture over here gives us what happens with your diverging lens. And for the diverging lens, it actually doesn't matter if your object is outside the focal length or if it was inside the focal length. You will always end up with a virtual image using a diverging lens. Right, so the thing you want to be careful of when you're asked about image formation using a converging lens is you need to pay attention to whether the object distance is inside the focal length of the lens or not. Right, if the object is outside the focal length, like in this first picture, you're going to get a real image. If the object is inside the focal length of your converging lens, you're going to get a virtual image.